Ms. Chi. And first of all, I would like to thank the officers of NLC, no, North Laguna chapter, for inviting me over. I think this is an absolute pleasure for me to speak with you regarding electrical safety for critical care units. It's something I'm very passionate about. But before we do that, I would like to welcome you also to where I am right now. I am actually in our engineering laboratory. This is where we usually conduct our trainings, our webinars, just because most of our equipment are here. And you see some of the stuff behind me. And right across the room is actually our insulating oil laboratory. No? So maybe we can show that. That's our insulating oil laboratory right there. So that's where we do dissolved gas analysis, oil quality run, and so on and so forth. And you would probably see somewhere hidden there is our chemist, Miss Hope, who does all the testing for the dissolved gas analysis. It's also another thing that we talk about a lot, no? Is dissolved gas analysis. So yeah, there. So now that we can start, I'd like to give you a heads up of what we're going to be doing today. This is not just me talking for the next couple of hours, no, about electrical safety in critical care units or hospitals. But what we will try to do is to actually give you a little bit of a demonstration, or I mean, in the absence of any hands-on learning, no. So what we're going to do is we're going to try to show you a couple of demonstration units. Now, at my back right here is basically a teaching box, no, for insulation monitoring devices for ungrounded systems, right there. And then on my left is basically a demo box of a system for operating theaters. So that's what it is now. That's exactly how it looks like. So what we're going to be doing is we will be discussing the fundamentals, the concepts behind it, the measuring principle, what to look out for, and then we'll go into all this. All right. Okay. So maybe we can start. All right. So I hope everyone sees my presentation. I would like to ask everyone, since I am not sharing my screen, please put me either pin my video or put me on speaker view or put me on spotlight, because I'm not sharing my video. I'm just clicking through my laptop. All right. Okay. So this is what we're going to be talking about. We're going to be talking about leveraging technology for safe handling of power. So it's basically understanding insulation monitoring and fault location for hospital critical care units. Now, this presentation will basically dig deep into the theory, application, and practice of online monitoring of insulation resistance and fault location for mission critical facilities in accordance to IEC 60364. Basically, IEC 60364 is a standard for protection against electrical shock. Now, this lecture will likewise discuss specific applications for DC systems, grounded and ungrounded AC systems, if we still have time, right? Now, to start off, these are the common things we hear, right? First off, we have a suspected ground fault, but we don't know where it is. In Tagalog, nag-trip yung GFCI namin. Okay, so GFCI is ground fault circuit interrupter. Nag-trip yung GFCI namin, tinaas na lang namin yung setting para wag mag-trip. Probably the worst thing you can do. Suddenly, you mess up your protection coordination. So that requires a different topic altogether, that requires a different study. All right? Now, there's another one. Laging nagtitrip yung ground fault relay namin. Tinaas namin yung setting para di mag-trip. Again, another problem. And there is a follow-up there. Nung tinaas namin yung setting, nag-trip sa main, nag-shutdown kami. Of course, we don't do that. No? Now, for the hospital application, this is what we've heard. Whenever we use a dialysis machine, patients experience the sensation of being electrocuted. So, ayun pala. Pwede rin pala mangyari even if we're using specific equipment in the hospital. So in this case, dialysis machine. Okay, so that's what we're going to be looking into. Now, outside of being electrocuted, we also have what we call, the fires. Now, according to the BFP, right? According to the BFP, and you guys all know this, there's no such thing as what we call a faulty electrical wiring, just because it's already working, right? Now, most of the time, what happens is, ang sabi ng BFP is overload. No? Once we start overloading cables or whatnot, what happens? Basically, we have thermal effects, right? And that starts the fire. Okay. And then next, we have a little bit of statistics here based on the NFPA. This one I got out of their website from March 2018. If you will see here, electrical distribution and lighting equipment basically make up for as much as 55% of direct property damage. Right now, another interesting fact here is this, where electrical distribution and lighting equipment account only for 24%. However, again, it's 25% of direct property damage. So that 24% that we encounter pretty much destroys half of your facility, right? So that becomes quite dangerous as well. And here's another one. Electrical distribution and lighting equipment, transformers and power distribution and power supplies accounted for just 7% of fires. And again, 46% of direct property damage. That 7%, if that happens, it eats up half your facility. So electrical safety is, of course, a big issue, especially for mission critical facilities, may it be hospitals or manufacturing or distribution or generation companies. Now, here is the scenario. Most of you gentlemen will probably be working or are working in a modern facility. Now, your demands on your electrical system is very high, right? So therefore, you need round-the-clock operation. This allows very limited time for preventive maintenance. Now, in Wesco and in VCP, the company I work for, basically, we do a lot of asset testing for power assets. I remember just a few years back where we had 3-4 days to test a couple of transformers. Now, sometimes we're given 8 hours to do 2 power assets. Suddenly, it's becoming a race against time. Why? Because people don't want to shut down. Because once they shut down, that costs them money, right? So, medyo humihirap ngayon pagdating sa preventive maintenance. Therefore, we will probably need some sort of monitoring to ensure safety, reliability, and efficiency of the system, right? Because at the end of the day, it's all about money, right? Now, later we'll talk about the kind of effects it has on business. Now, the causes, whenever you have continuous operation, this can result in premature aging of electrical components. And of course, failure to acquire predictive and preventive maintenance data can result in catastrophic process and economical impacts. Now, if I ask you, ladies and gentlemen, how many times do you want to shut down in a year? Especially those unwanted shutdowns, right? Nobody wants that. Now, if you have unwanted shutdowns, especially if you're in manufacturing, one is that sometimes you waste raw materials. Second is that you probably damage equipment, right? Even worse, sometimes someone gets injured or worse. And lastly, how much will it cost you if you don't get product to market? How is that going to affect your market share, right? So again, at the end of the day, it's all about money and how it gets down there. No? Now, if you go to hospitals, how much trouble do you think if your power supply in your operating theater, regardless whether you had the UPS and redundancy of a generator, if your system shuts down while someone is on the operating table? No? What is it going to cost you if one of the medical practitioners actually gets hurt because of electrocution? Or worse, the patient. Diba? So all these things we need to consider whenever we're designing or maintaining our power system, especially for critical care units for hospitals. Now, what are the effects of deteriorated insulation? No, we hear this a lot. We hear short circuits. A lot of times it doesn't really happen, not too much. No. Then you have short circuits to earth or line to ground faults. If you are on an ungrounded system and leakage capacitance is not that high, chances are it's not going to trip right away. Perfect example are the ones in DC systems. You know, you have a hard fault to ground, it just keeps on running. However, there will be a voltage shift to ground. No? And then you have the short circuit to expose conductive parts. This is something more capacitive in nature, and we will be discussing leakage capacitance as we go along. Now, here's a little bit of statistics. Now, these statistics are quite old. I think this is 2004. I picked this out intently just because it was the most significant that I've seen. No? Now, the common causes of fires are usually the fixed wiring. These are the ones in your walls, no? Yung mga naka-roughing ins. And these make up 34%. For households as well as hospitals and manufacturing, 17.2% is caused by cords and plugs. Again, why? Kasi kuminsan pag binunot natin yung mga plug, kinukuha natin galing dun sa cable and not the plug itself. No? You have lighting fixtures as well that makes up 12.4%. However, these are usually high bay lighting, the one with lamps and high-powered ballasts. No? The LEDs are not as susceptible, but then again, it really depends on the kind of LED drivers you have. If those LED drivers are not well built, then they can cause fires as well. Switches and receptacles, just because you all know that when you have a high resistance contact between your switches, receptacles, or circuit breakers, they introduce thermal effects as well, and they can catch on fire. Okay, now what are the common fault influences? Oh, by the way, let me just go back here. If you see this thermal image right here, right? If you see that thermal image right there, there is going to be a story behind that later as we go along. Now, what are the common fault influences? First of all, you have the electrical influences. Whenever you have overvoltage, overcurrent, harmonics, lightning, magnetic, and inductive influences, therefore, if you have lousy power quality, chances are you also compromise the integrity of your insulation. Because what happens to a particular load, a cable, a bus bar, a circuit breaker, whenever you have overvoltage? They usually heat up. How about whenever you have overcurrent? Same thing. Whenever you have harmonics, if you have high level of current harmonics, then it also heats up a particular load, a particular protective device, so on and so forth. And the rest of it is the same, right? Now, mechanical influences, whenever you have shock, impact, installation flow, penetration of foreign bodies. Environmental effects, temperature, of course, where we are, where we live, it's not the coldest part in the world, no? Now, if you have a lot of moisture in the atmosphere, no, of your workplace, let's say tabing dagat, or at the same time, that atmosphere is also corrosive, right? Whenever you have chemical influences, in operating theaters, their cleaning solutions are quite corrosive as well, kasi medyo matapang. No? And then you also have pollution and pests. Now, the pollution, basically, this creates some sort of capacitance as well between the conductors and sometimes to ground. Now, depends on how bad the pollution is. And of course, the pests, I don't know why the rodents love the cables, they love nibbling on it. No? And then you have equipment aging, and lastly, you have unsafe practice. Now, these two guys on the picture, the guy sitting down, that's Helmut Mumm, and the guy standing up with a beer is Wolfgang Hofheinz. These are the gentlemen, this was during training in Germany, these are the two gentlemen that actually developed the residual current monitoring system. And this was their version of trying to prove to us that it actually works. And they asked us to join them. We said no, so we just took pictures. So I guess that all of you will agree with me that insulation resistance is the decisive factor for a safe, reliable, economical, and continuous operation of any electrical system, right? So I guess you all agree with me there. Therefore, insulation faults should be number one, detected. Sometimes this is easier said than done, near impossible. Depends on the size of depends on the kind of system you have and on the size of system you have. Even worse, if we, okay, for some strange reason that you guys found it, and then your boss tells you, okay, uh, you detected it, go out and find it. Location is also very difficult. One of the easiest thing to do when it comes to insulation faults is to actually eliminate it. Why? Just because something happened already. You know where to go. So these three things, remember this: detection, location, and elimination. Those things are very, very important whenever we're trying to monitor or trying to look for insulation faults. So, system classification. We'll be talking about a couple of things, basically just ungrounded and grounded systems now, based on monitoring. Now, you will see down there, it's called the IT system. So that's not information technology, that's actually isolated Terra. Terra is ground, isolated, that's how it's connected. So it's isolated Terra. It's ungrounded, some call it floating or isolated. All right, so it's isolated Terra. The grounded system come in different versions. You have the Terra, coupled Terra neutral, so on and so forth. Now, what is the difference? Chances are all of you guys know this already. No? Now, which among these two diagrams are actually ungrounded? If you said that one, then you are correct. That would be the IT system. Now, both of them are on a Y secondary, right? No, commonly we know the ungrounded system usually as a delta system where the ground is floating. But in this case, you're going to be on a standard 5-wire system where you have line 1, line 2, line 3, and neutral, and there is no direct connection between live or current carrying parts. That means that grounded system that we see on the screen right now, that's usually what we see in the Philippines, that we call that bonded, right? All right. Now, as I mentioned, the IT system has no direct connection to live or current carrying parts. For the grounded system, the neutral conductor and the ground conductor, PE, are connected at start point. Okay, so basically, that is the main difference where you don't have direct connection to live or current carrying parts. Now, next question will be, which one is safer? All right, which one is safer? Can I ask anyone out there to just answer which one do you think is safer? Anyone can answer. I'd like to hear from you. Which one is safer? Go ahead. Which one is safer?
Grounded.
Grounded. All right. Grounded. All right. Excellent. Thank you very much. Right. Grounded system. That would be usually the answer for us. But maybe I'm not contesting what you answered because that's absolutely correct. But it really depends on the kind of design. So probably the most politically correct answer would be, it would be application dependent. Now, you did answer that it is grounded, and I agree with you completely. Maybe in your facility you have expensive automated equipment without a lot of human intervention. Then if there is a line to ground fault, something goes wrong, you want it to trip to save the equipment and whatnot, right? Great, that's fine. However, how about in hospitals? How about in hospitals? Now, there is a little known fact that operating theaters, operating rooms for that matter, has to be on an ungrounded system. Why? Because in an ungrounded system, dependent on the leakage capacitance, in an event of a first fault, of an asymmetrical fault, right? Of an asymmetrical fault, just meaning one line to ground, the protective device will not open, right? Dependent on leakage capacitance. And in fact, this is already in the standards. It is already in the standards. If you want to look the standards up, it is already in NFPA 99. It is in IEC 60364-7-710. And it is even in our own PEC code, which is Article 5.17, right? All of which point to an ungrounded or isolated or floating system monitored by an insulation monitoring device for IEC, or a line isolation monitor for either NFPA and PEC, just because we kind of copy pasted, the 2005 NFPA, no? But all of which point to an ungrounded system where you have an isolation transformer, an insulation monitor or line isolation monitor, and an annunciator, right? So basically, for hospitals, it is well, it's not even recommended. It is in the standards that we run on an ungrounded system. So it greatly depends on the application and the design. Okay? Why did they put that on the hospitals? Why ungrounded? Because the fault current in an ungrounded system or an IT system is low in an event of a first fault. The protection device will not trip in the event of the first fault. That's why they use that on hospitals. However, in grounded system, there's a high risk of current passing through the body. The touch potential is primarily limited by the body impedance. We're usually about 400 ohms. About the regular body size, about 400 ohms. So here's just a few more examples on that. All right, let's not go into that. It's practically the same. Now, what is the effect of leakage current to the body? We have here 0.5 milliamps. This is according to IEEE. 0.5 milliamps is the threshold of perception. Ito yung nararamdaman mo na. Threshold of perception pa lang. 5 milliamps exposure to about 10 milliseconds. That would be your let go threshold. Yun napapabitaw tayo. And 5 milliamps is the absolute limit, no, for hospitals as well. The leakage current in hospitals should not reach 5 milliamps. In fact, line isolation monitors and insulation monitoring device will create an alarm at 1 milliamp already. Okay, 1 milliamp may alarm na yan. So 5 milliamps, you definitely have a problem. All right. Now, at about half a second exposure to about 20 milliamps, that would be respiratory paralysis, fatigue, and pain. Again, depending on your body impedance, exposure to about 70 milliseconds, anywhere between 70 milliamps, about half an amp, ventricular fibrillation. Ventricular fibrillation is yung bumibilis yung tibok ng puso. Now, this last bit isn't exactly in the IEEE, but there was an article that I was reading, so I decided to put it here. So I do have a disclaimer that this is not in IEEE, but really there's not a lot of things known to what happens to the human body beyond 1 amp exposure, no? But what they've studied at about a second and a half, you can have sustained myocardial contraction, burns, internal organ damage, and loss of muscle ability. Now, I did ask a doctor what a sustained myocardial contraction is. What it is, once your heart contracts, it doesn't uncontract anymore. So we kind of know what's next, right? So how do we protect ourselves, or how do we monitor the integrity of our insulation for ungrounded systems muna tayo, right? So you have the insulation monitoring devices. Right. The insulation monitoring devices, that you have two versions of that. One is the one you can use for AC, DC, for industrial, no? And the other one is the hospital kind of insulation monitoring device. Now, the insulation monitoring device for hospitals does the same thing, but has a few more other connections, which I will explain later. Then you have the line isolation monitor, and this is the device that they use for NFPA, right? And then you have residual current monitoring device. You have insulation fault location systems, overcurrent protective devices, and residual current devices. RCDs is what they term GFCIs, ground fault circuit interrupters, in Europe. In Europe, they call it RCDs. In the US, they call it GFCIs.
Kung bibilhin ko lang naman yung cake at saka barbecue. Barbecue, wala pa.
All right. So why do we monitor in the first place? Right? Why do we monitor in the first place? Now, of course, you want to make sure that personal protection, plant protection, and fire protection is not compromised. Now, the regular insulation monitoring device, right out of the box, right out of the box, is that it will make its first alarm at 40 kilo ohms. And the critical alarm based on IEC is set at 10 kilo ohms. Now, the difference between the 10 kilo ohm alarm, which is the critical alarm, and the 40 kilo ohm first alarm is basically our advantage in time. where you can perform scheduled maintenance, right? So, well, insulation basically does not deteriorate like yung pinutol, di ba? They deteriorate over time, right? They deteriorate over time. I've been asked a lot of times, what if kinagat ng daga? Then yeah, we can find it. However, it's just the deterioration will just be faster. No, because uh, ang daga hindi naman pagkagat putol. No, it's gonna nibble on it. Therefore, your insulation will basically deteriorate over time as well, right? So the main advantage is your advantage in time. You can then schedule maintenance, no, for your facility. Now, the insulation monitoring device was actually invented by Mr. Walter Bender. No? Now, Bender is a brand of insulation monitoring devices, and they are the pioneers. They're basically the inventors and market leader for insulation monitoring devices and residual current monitoring systems. Now, a little bit of a backstory on Mr. Walter Bender. He used to be a mining engineer during Nazi Germany. So his job was to actually monitor light bulbs. And this is how it was connected, the 3-bulb method. That was, they monitored insulation back in the day. So since it was a mining facility, it wasn't an ungrounded system. So they connected bulbs, line to ground. And then, whichever bulb actually flickers or lumalabo or even namamatay, they know for a fact which phase is actually having a problem, no? So that's great. Its shape, it's somehow effective, no? And then, of course, with the same concept, you can use the voltmeter method. So, if you have your regular power energy meter, right? If you had your regular power energy meter and you connected it and it's on a delta, then one of your lines drops down, and then you measure voltage on your ground, you know for a fact that that particular phase is actually the one with the fault, right? So, however, this old method, that's why we call it heritage. Now, this old method was great for pure sinusoidal AC systems. But now, when you have active harmonic filters, you have capacitor banks with reactors, you have variable frequency drives, you have inverter TVs, you have a hell lot of computers, you have a lot of nonlinear loads, LED lights and devices, no? Then we also have distortion on that sinusoidal waveform. And these things do not react well to that. And that's why they came up with the insulation monitoring device. Okay, so what is the measuring principle of an insulation monitoring device for an ungrounded system? So basically what happens, that it takes the value of 1 ohmic resistance fault to ground, that's being monitored, and the absolute insulation resistance and the sum of all ohmic resistance fault to earth being monitored, and this is measured via through RMS, no? So basically, it's just somehow a modified Ohm's law. Hindi pa rin naman nagbabago yun, it's still Ohm's law. Now, this is a basic block diagram of a typical insulation monitoring device. You have a generator that generates your carrying voltage, no? That carrying voltage, as per standard, is not supposed to be more than 25 volts DC. The system, you see that no? The system should be able to measure its own internal resistance. You have a low-pass filter to take out some of the noise. You have coupling resistors to create a superimposed DC loop voltage, right? Now, basically, what happens is that when an insulation fault between system and earth closes, the measuring circuit, a measurement current IM is flowing. No? That IM is variable. You can set it from the device. It could be anywhere between 1 to 50 milliamps, depending on your protection goals. No? Now, that current causes a voltage drop proportional to the insulation fault at the measuring resistance. So again, it's still Ohm's law. No? And that's how we are able to measure insulation resistance online. Now, kanina we were talking about measurement of leakage capacitance, why this is important. This is the reason why, because now we already have either nonlinear loads, we have frequency variation, and so on and so forth, right? And we will have DC components. We will have pure AC sinusoidal waves, and we will have a combination of both. And sometimes a lot of those superimposed DC voltages that is introduced into the AC circuit, it gives us a little bit of problem sometimes, no? So insulation monitoring devices look into the measurement of the 50 or 60 hertz section. They look into the DC intermediate section, and of course the motor area or the load area. There you go. So you have interference rejection, you have DC fault elimination to clean up its own measurement, right? Now, how do they compensate for this? No? Because superimposition of DC voltages, of course, has its limitations. Now, the limitations, it's great for pure sinusoidal AC, which is next to impossible nowadays. Now, if there is an induced DC leakage current there, DC voltage induced into the AC circuit, this kind of forces the measuring voltage to shift around the 0 point. Now, when you think about this, you have that pump. It actually studies that, shifts that accordingly, and it actually acts kind of like some sort of an active filter where it tries to cancel out. It cancels out that capacitance. Why? For it to be able to measure properly. Now, since we're at the topic of leakage capacitance anyway, how does it influence your measuring? First, you have natural system leakage capacitance. And this comes from your cables, your wires. We know for a fact that there is no perfect insulation. You have your design. So for the photovoltaic, maybe you have wind, you have whatever. And then the system size. The bigger the system, the higher the leakage capacitance. And then you have the artificial capacitances. When we talk about the anti-noise capacitor, this could be either a passive harmonic filter or an active harmonic filter, or it can be an electromagnetic, an EMC filter. Either way, it is artificial capacitances. Okay? Now, when you look at this, I have a little bit of a formula here. Of course, you guys don't have to do this. You don't have to do this. Your system will do it for you. But we need to understand how much capacitance we have in the system. Why? It will influence. It will actually influence the length of time before an insulation monitoring device can actually give you a measurement, right? According to the IEC, an insulation monitoring device should be able to give you a measurement in 30 minutes for high leakage capacitance systems. 30 minutes, ang tagal nun. But just because of leakage capacitance, it really does take time. And there have been instances where poorly built insulation monitoring devices failed to give a measurement at all. So you have a little bit of a formula here. As you can see, the higher the leakage capacitance, the higher the leakage capacitance, the longer the time, right? So we have to be aware of that, and especially for critical care units for hospitals. It is actually limited to 10 kVA. The isolation transformers cannot be more than 10 kVA. Why? Just because we go back to this, the natural system leakage capacitance, the system size. Because beyond 10 kVA, they've determined that leakage capacitance increases already. And in hospital care, in critical care units of hospitals, you need the measurements almost instantly. Okay? So, we have here what we call a traditional KO meter for DC measurement. They're basically crude needle meters. They work perfectly on asymmetrical faults. When we talk about asymmetrical faults, it's just one fault to ground. It's either the positive side or on the negative side. However, when the faults become symmetrical, more often than not, they fail to work. In fact, again, this is also in the standards. Again, it's IEC 61557-8, where an installation monitoring device should be able to tell you or discriminate whether the fault is symmetrical or asymmetrical or both. No, whatever. It should be able to discriminate from that, positive or negative or both. Okay, so there. Now there it is. There. Sorry, kind of jumped myself there. So, what are the effects of extraneous DC faults in an AC system? We'll talk about AC system for now. Now, those DC faults render your GFCIs and RCDs unreliable, increasing exposure to fault currents beyond 50% of the set point of your GFCI. Why? Because the typical GFCI is not DC sensitive. Okay. Also, extraneous DC voltages can appear in the fault path, creating a false insulation resistance measurement if you're already using insulation monitoring devices. Also, those DC fault currents beyond 10 milliamps can falsify reactions of PLCs. And of course, failure to isolate DC faults can result in pre-magnetization of relay contactors and affect the reliability of your AC protection system. So we need to take care of that sometimes. And here are a couple of examples really where you would find DC faults. No? DC faults are influenced by loads with thyristors, rectifiers, and frequency variation. Now, for the usual variable frequency drives that you guys probably have in your facilities, no, they're usually not coming from the power supply stage or the IGBT stage. They usually come from the noise filter. Now, that's the one that gives out those DC leakage capacitance, right? Okay, so there you go. So there you go, the noise suppression filters. Now, here is basically a conceptual model of insulation monitoring. Now, let's say you have this kind of system. It's an ungrounded system. So this time it looks like we're on a delta system. Let's say you have a couple of loads and you have your insulation monitor. Now, the connection of the insulation monitor is basically just on the secondary of that transformer, right? And as you can see here, you do not need more than one insulation monitor for one system. Why? If you will recall the block diagram I showed you a few slides back, where the insulation monitoring device has to be able to measure its own internal resistance. Just because take out all those devices inside, what it is just a short circuit. So it has to measure its own internal resistance. So if you had two insulation monitoring devices in one IT system, then either one of the devices will measure the other one as a fault. Okay, so you only need one. All right, so there you have an insulation monitoring device. Now, let's say we encountered a fault right here. What will the system tell us? The system will immediately tell us that you have an insulation fault and will give us an insulation reading, right? And right now, measuring in true RMS, they tell us, hey, it's already at 10 kilo ohms. Okay, if you remember the things we have to do for whenever we have insulation faults, number one, detection, number two, location, and number three, elimination. Problem number one, detection, solved, because we already know that we have a problem. However, what if this system is relatively big? Where do you find it? How do you find it? And that's the time we start using insulation fault location systems. Now, these insulation fault location systems are basically boxes that evaluate the fault, right? Now, at least for Bender, what they have is a 12-channel fault locator. And then it comes with its own proprietary CT. There's zero sequence CTs where you have all three phases inside, no, except for the protective earth. Now you have 12 circuits, and you can go to as much as 1,180 loads, such as, I think that's about 90 fault locators. No, that's about 90 fault locators. You can have that. And then what happens, since if you have this fault locator, the system can automatically send out a pulse. Remember, we need a pulse current. Now that pulse current can anywhere be between 1 to 50 milliamps. It's basically only the hospitals that use a 1 milliamp pulse current. But for the industrial use, it can be anywhere between 5 to 50 milliamps. A good starting point would always be about 15 milliamps. Now, once that pulse has been deployed, no, whichever CT actually senses that pulse, right? It kind of tells you which circuit that is. It tells you the address of that device. In this case, the yellow box is address number 2. The channel on that device, I think this is channel 3. And then the actual residual current that was measured, which is about 13 milliamps, giving you an exact location of the circuit where you can check. So that is fault location right there. So if this were a DC circuit, no, if this were a DC circuit, what's going to happen is basically it's going to tell you whether it's on the positive side or on the negative side. And it will give you the exact location where it is. Now, that would be basically the way, a conceptual model of how it works. The measuring principle is going to be exactly the same for critical care units of hospitals, only with a few differences in terms of specifications and thresholds and limits. Okay, so we now go to the hospital critical care unit power supply. Of course, there are a lot of issues for hospitals, no? And all we're going to be dealing with right now is patient safety. Now, actually, is below patient safety. One of them is patient security as well. Electrical safety is one of them, and other safety stuff. Why is patient safety is very important in hospitals, particularly for critical care units and neonatal care, no? It's because even the smallest currents flowing through the human body put the patient's life and health at risk. And of course, the availability of the power supply must be guaranteed even under fault conditions. And that's the main reason why they're deploying ungrounded systems for operating theaters. Now, what are the standards? As I mentioned a while ago, you have the Philippine Electrical Code, that's Article 5.17, which we reference to NFPA 99. We have the IEC 60364-7-710. And then you have the NFPA 99. Now, basically, the IEC, it kind of defines the fundamental principles and concepts of electrical wiring installations in medical locations. The NFPA, it basically establishes the criteria of healthcare services or systems to minimize the hazards of fire, explosions, and electricity. Now, they use two different things. No? The IEC uses the insulation monitoring device, and the NFPA basically uses the line isolation monitor, right? But both of them will have isolation transformers. Now, let's go into the details, of the differences between an IEC monitoring device and an NFPA monitoring device. The one on top is basically the line isolation monitor. No? Now, let's just look into that first. No, they work basically using measurement voltage and current. The line isolation monitor, take note, calculates the fault impedance and calculates the hazard current. So that term right there, calculates. No? So what happens if you start plugging in equipment to that particular OR? Of course, hazard current goes up. The way it measures is parang GFCI din, parang residual current din. Where if you have a non-zero balance of currents, it starts acting up. Therefore, sometimes that risk may or may not exist just because it is calculated. That's the only caveat when using the line isolation monitor. I mean, honestly, we sell both systems, but if you start asking me, I'd rather have a direct measurement rather than a calculated measurement. Okay, so that would be the main difference. Now, physical differences, as you can see, one is the size. The next one is the way it is installed. Now, the line isolation monitor is basically installed directly in front of the transformer panel. within the operating theater. So you have your whole panel inside the operating theater. You have your circuit breakers there. You have the line isolation monitoring there, as well as the transformer. No? Now, you probably all know transformers, these are dry type. Chances are you will need to maintain them at one point, right? Yeah, you're gonna have to clean them at one point. So the maintenance guys, now the maintenance guys cannot just go inside operating theaters with their with their dirty safety shoes, no? So it's gonna have to be a clean room. I mean, you're gonna have to open up panels and take out the transformer, clean them and dry them out, and sometimes even purge them with nitrogen or whatever. Uh, and that becomes a pain in the neck, right? Um, how, the reason why, one of the, well, the main reason why it's directly mounted in front of the panel is because of, I'll go back a couple of slides. I'll go back a couple of slides, is because of this, cables and wires, the distance and length of cables and wires. It cannot handle longer distances than that of right in front of the panel. No, it can go further than that. So let me just go back to my, let me just, sorry, let me just go back to my presentation right here. There you go. There. So again, it's calculated, no? So that's one of the main problems. You're gonna have that whole panel, and of course, you will have that 60 hertz hum that you will hear inside the operating theater. Uh, Also, the total hazard current is a calculated result, thereby susceptible to load conditions, right? Especially if you have the bigger hybrid ORs. That's what they call it nowadays, where you have other equipment in there. No, so whenever you have other equipment, bigger load equipment, and then you start introducing DC leakage capacitance as well. Now, let's go to the IEC insulation monitoring device. As we mentioned a while ago, the way it measures, in the measuring principle, it's basically a direct measurement of system impedance through the use of measuring pulse currents and superimposed voltages. It can be installed in a remote location where only the annunciator alarm panel is visible in the operating theater. Let's say the operating theater is on the third floor and you have an electrical room there. That's where the isolation transformers can be, as well as the insulation monitoring device. And all that's gonna show up basically in the operating theater is the annunciator, right? Yun lang. So it's nice and clean. You have your alarms, and you don't have to, you're not going to have to worry about leakage capacitance. Okay. Now, of course, due to the measuring principle, accurate measurement is achieved independent of loading conditions. What we're looking into really is insulation. Even insulation of the equipment itself. If you plug something in there that has bad insulation, we will find out. You will find out. It will give out an alarm. And a more visual comparison, this is on the left side of your screen. That's basically how a line isolation monitor panel looks like. You have the circuit breakers, you have communication there if you want to. And then you also have the transformer. As you can see, it's a very small transformer. No, it's a very, again, no more than 10 kVA. Now, for the line isolation monitors, for the insulation monitoring devices, you have that little yellow box. You have that little yellow box. You have the isolation transformer, which is again no more than 10 kVA. It will have a temperature sensor. This is the same as the line isolation monitor. You will have a small temperature sensor. You will also have a small CT to measure load, to measure current. Why is this important? Because this is going to be part of the alarm. This is also one of the differences that you have from the industrial kind of insulation monitoring device and the hospital grade monitoring device. Here, you have connections for load monitoring as well as temperature monitoring of the transformer. Why? Remember, you only have 10 kVA. It's a small transformer. It's going to be easy to overload it. And you guys know for a fact that a nice way of loading your transformers would be around 80%. That's where it's most efficient at. Okay, so again, you can start installing that transformer outside of the operating theater. Okay, and you have a control panel going towards the maintenance guys or the nurses station or wherever. Now, this is the kind of system that you have or will need if you are going to be on an IEC compliant, I would say, system for your operating theater. You will have your isolation transformers, right? Again, no more than 10 kVA, 1 kVA to 10 kVA. There is specific isolation transformers for OR lighting that's separate from the operating theater system. No, you will have your insulation monitoring device. Again, the injected current is less than 1 milliamps, and the indication will be below 50 kilo ohms as compared to the regular ones, which is 40 kilo ohms and 10 kilo ohms. Here, with the hospital insulation monitoring device, anything below 50 kilo ohms is a fault to them. All right. Okay, so and then you have what we call the remote alarm indicator, right? So that's the one that's showing up on your OR theaters, and that's the one that's giving out the alarm. In fact, that particular device can also accept 12 12 channels of dry contact inputs, also for alarms of, like, let's say, oxygen or whatever gases that you might have that has sensors on it. Okay, so what I will be doing now is to actually give you, before we go to the case studies, no, what I will be doing now is actually give you a little bit of an idea how it kind of looks like in a demo box, so to speak. So I will be getting out of my seat and show you exactly what I have right here. Okay, so you guys don't need to see me, but what I have here is this is basically right here is the insulation monitoring device. So it's small yellow box, right? It's a small yellow box that's DIN rail mounted. I should go here because I can't see what I'm doing. And then what we have here is what we call the EDS 461, or an insulation fault locator. And this is an older gateway that we have. And this is the annunciator, right? And this is another fault locator. It's a small 6-channel fault location system. Now, if you guys look into the diagram, of course, you have an isolation transformer. I have a temperature sensor right there. I have a CT for the load, and I'm just connected via a 2-wire. We call it the BMS, a bender measuring system. It's basically a 2-wire TF cable, twisted pair. They just daisy chain to each other there. And then right now, what's happening is I can actually connect it to the internet or my laptop. Now, maybe we can show the laptop screen. So there, it does not require internet access, just a network. Okay, so we can go back to the demo box already. So, why is the connection to the laptop important? No, why is that important? Just because your maintenance guys will not be inside the OR. They're not trained for that. They might just faint in the in the presence of blood. So you can have that and have it monitored in the safety of your offices or through your mobile phone and whatnot. Okay, so again, the insulation monitoring device, you have that here. You have the fault locator, you have a gateway, and you have the annunciator in another form of insulation monitoring device. Now, basically what I will do now is I will simulate a couple of faults. No, one is what I will do is I will overload the system. So almost immediately you will have some sort of alarm coming out of the annunciator. Now, if we can just zoom in on this. Yeah, can we zoom in on that? Can you go in there? Just focus on that. So I don't know if you guys can read it. If you guys can read it, it says temperature, transformer overload, and temperature set. Transformer overload. So of course, whenever you have a transformer overload, temperature will rise as well. So if I go switch myself to the monitoring system, as you can see here, I have the ISOMED. That's the insulation monitoring device. If I click on that, it will tell me that sure, my insulation resistance is fine. I still have greater than 1 mega ohm, My initial load was about 44%. Yeah, okay. And then the next one is over temp. Well, I hit over temperature. No? Then the next one is that it tells me that I have over temperature. So why did that happen? Right? So I can turn that off. As you will see, if I start turning this off, even if I turn off the fault, the alarm almost never goes away. Well, what I programmed, if I turn off the alarm, it turns off. No, but generally, it is already stored inside the system as a fault. Right? Now, we'll try another one. Now, this time, it's going to be overload instead of an over temperature. Let's see if that works. If the switch actually works. I don't know if it works. Oh, it does. So, if you come in there, can you focus on this? There you go. It tells me that I have an overload. It tells me the time and by how many percent. They say that I put in a load of about 110%. So I'm overloading the transformer, and we don't like that. Chances are, if that is actually correct, that I'm loading it by 110%, right? If I'm loading it by 110%, even the temperature sensor will go off. The temperature alarm will go off. All right. So let's see if that shuts down on me. Yes, it shuts down on me. So what will I do now? What I will do now is actually create some other faults. So let's see. Remember, we're talking 1 milliamp fault location, right? 1 milliamp fault location. The system, the insulation monitoring device already determined that I have an insulation fault. It's the fault locator's turn to actually find it. So right now, it's telling me that chances are I have a fault somewhere on channel 1. There. Now, to make sure, I want to find out, I'm going to look into my system. I'm going to look into my system. I'm going to check on, guys, by the way, I apologize. My software right here is the old one. All right. It's the old one. So the ISOMED tells me that, yep, you have an insulation fault. All I have to do now is actually try to find it. So here, the ISOMED tells me that it is on channel 3, and I have a 500 microamp. Microamp, right? 500 microamp fault. It's a small fault. That's how sensitive it is. Why is it? Why is it that sensitive? Just because during open heart surgery, right? During open heart surgery, you can disrupt the frequency of the heart by just 10 microamps. And if you look into the electrical safety devices that they use to test those medical equipment, you will actually read that there that they have measurements for 10 microamps. So that becomes very important. Okay, so I hope everyone got that. Uh, I will turn off the faults because it's quite annoying. See, it's not stopping up until I mute it. All right. So once again, what you guys would usually have for an IEC compliant system, you will have a transformer, right? You will have a transformer that's no more than 10 kVA. There are specific requirements for those transformers, no? In terms of the inrush current and no load conditions, no? It's very specific. It's specifically made for medical applications. You will have an insulation monitoring device. The fault locator is optional. No, that is optional. And then you will have the annunciator, right? You will have this. Uh, kind of like a call button. Now, transformer, insulation monitoring device, annunciator. But since you're there anyway, though again it's not required, I would have, especially if you had a lot of ORs, I would have a gateway. So at any single time there is a fault, the maintenance team or the whoever's in charge of maintenance of your equipment or your electrical system is informed. Again, your advantage is advanced information here. No, it's not how good you are at diagnosing a problem. It's you finding out earlier than other people. Okay, so let's go now to the case studies. Here is a little bit of a case study that we've actually installed this, right? So it's 5 ORs, all of which are 10 kVA. Now, it is a case study, but this is absolute. I mean, in terms of compliance, it's not exactly compliant to IEC because when we talk about the annunciator, which is that one that gray. If you can see it, the MK2430 annunciator nurse station. Now that's in the nurse station. What the IEC says is that it should be in each operating theater, each, right? So, well, the budget wasn't as big, but they kind of ran out of that just because uh, the installation of the isolated the power supply became an afterthought. It was put in, it wasn't part of the original design up until we informed the owners, and then of course each individual room will have its own insulation monitoring device. These things are located on the same floor but in a different room altogether, including the fault locators, right? And then you have, we call that the COM 465. It's a gateway. So basically, the maintenance guys can start looking into the system wherever they are via their laptops or devices. They just connect to the network that is in the system. So here, what happened is their IT department decided not to actually put it in the same network as the internet. So it has a dedicated Wi-Fi network. No, it has a dedicated Wi-Fi network, so it doesn't have to go to a lot of stuff. Now, here I have a rather simple case study. This is for a DC circuit. So what we had is an insulation monitoring device. No? Now, the insulation monitoring device, again, as I've mentioned a while ago, can already discriminate between positive or negative, right? Whether it's a symmetrical or asymmetrical fault. But the application that the customer wanted to find out how much of that voltage shift was actually going to ground. No? So what we did is we just included a voltage monitoring relay. No? So we didn't use the trip units. We didn't use the dry contact outputs to trip anything. We just used it to measure voltage of the DC circuit. And since it has a small footprint that is similar to the IMD, meaning the insulation monitoring device, it was a perfect fit for a small panel. Another DC application was using the newer ISO 685. Now, pretty much what I shown you a while ago, which is the insulation monitoring, or the measurement of insulation. This one will have a few graphs, and it will tell you whether it's on the positive side, negative side. And if it's on AC, it's going to tell you whether it's on line 1, line 2, or line 3. And it will tell you the actual voltage shift to ground, right? So in this case, you have positive, there's a couple of pictures there. Is it positive or is it on negative? And it's going to tell you the kind of leakage current that you have for that particular line. No? So it becomes very effective. Now, if you remember a while ago that I dependent on the leakage capacitance, that the IEC actually tells you that an insulation monitoring device should be able to tell you, give you a measurement in 30 minutes, right? This thing can do it in 8, even in the highest leakage capacitance systems, 8 seconds. It can do that. So I am almost done, but what are the advantages of monitoring and fault location? First is that you have direct measurement of insulation resistance of the entire system. It eliminates the guesswork in locating insulation faults. You have readily available predictive and preventive maintenance data. So it's kind of like the first step for asset management. You can have a visual or audible alarm. You have the capability to monitor your system from a remote or local position. and you will have the ability to send critical data to the right persons at the right time. Just because whenever you connect it to a gateway, although none of my customers ever used it, it can send out a text message. No, it can send out a text message or up to 10 emails, but usually it's 2, 3 emails. So it can get that information to the right people at the right time. Okay. Now, here's a little bit of an actual snippet, no, an actual snippet of a test result using using a portable fault locator. Okay, so if you will see here, which one would concern you a lot, no? Give you a hint. It's right there. 1 amp, no, on the lighting panel. So we followed that downstream. We found it. Downstream further, found it again. However, we were not able to go down further because we were not allowed to. No, but at least we know for a fact where it is. Lighting electrical room 2. So there. Now. Next, this is something a little more domestic, right? This is something a little more domestic. This thermal, I'm a level 1 thermographer, by the way, no? So it just so happens that I came home from a from a thermal shoot, and then so I had the thermal camera with me, and I had this insulation fault locator, portable insulation fault locator with me. So pag uwi ko, sabi ng kasambahay namin noon, sabi niya, sir, nakuryente po ako. No, nakuryente po. Sabi ko, saan? So there, when I broke out the thermal imaging camera, take a thermal image of it. That is actually a plug of an electric fan. So it's beyond 53 degrees. So obviously, a plug that small will not be able to handle that much temperature. And you don't see it all that much, no? It's still halfway in the CO, the convenience outlet, because nakuryente na siya. And I don't know if you can see it. There's an image of that plug there na medyo may sunog na. That's where she actually held the plug, no? And she was barefooted kasi when she tried to unplug it. And I did measure it while it was still plugged. I measured the 182 milliamps. So if you remember what the 182 milliamps happens to you, it's basically ventricular fibrillation, right? So there, ventricular fibrillation. So that's what happens. So that's something that's a little more that's something that's a little more domestic. Okay, so that is pretty much it for me. Let me check if I still have a couple of. Yeah, that is it for me. That is it for me. So I hope you guys were able to pick up a few things. And sure, if you have any questions, I'll be ready for questions.
Have any questions?
Sorry, I don't have access to that. I don't really have access to the chat box. I can't reach them from here. So I don't know if someone asked stuff from the chat box. So if you don't mind helping me out with the questions.
Okay, I think I saw some questions here.
All right. Can you turn up there?
Sir, please clarify, in one fault locator, are there 90 circuits that can be monitored?
Oh, yeah. 90, basically it's 90 by 12, right? So each do I have a, I don't have one here. Let me just show my slide again, just to, where is it? All right, let me just show my slide again. So this is the one, right? You were mentioning about the fault locator. Just give me 1 second. This takes a while. All right, that yellow box that you see there on your screen, that device is capable of 12 circuits, no? 12 circuits. Now, in one system, you can have as much of 90 of those devices. So it's 90 times 12. So 90 times 12 is about 1,100. Tama ba? Sorry, I'm going to use a calculator na. Sorry, 1,080 loads. It's 1,080 loads. It can handle 1,080 loads, no, in one system. So you will have 90 of those yellow devices, and then you can monitor up to 1,080 loads. Anything else?
Okay. Wait, I'm still checking.
Sure.
Sir, what are the requirements for the backup power supply of the monitoring system? Will a UPS suffice?
Yeah, yeah. Uh, a lot of times, I've seen a couple of systems. Well, this is abroad, no, not locally. Uh, the insulation monitoring. Sorry. Can I get the question again? I might have misunderstood.
The requirements for the backup power
Oh,
supply of the
backup,
monitoring. Yeah.
backup power. Well, I'm not I'm not a big designer, so to speak. But as far as I know, for hospitals, a generator is required. It's necessary, 100% load. And then what I've seen lately, um, especially outside of the country, and even the bigger hospitals that we have, is that they have 100% UPS, no, as a redundancy, just because sometimes generators will need some time to go up to reach up to speed, no. So what will happen is the UPS, right? The UPS will take charge, no, for 100% of that OR, for a couple of UPSs maybe, will take over 100% of that OR up until the generator comes up to speed. And then once it comes up to speed, it will switch back. It will switch to generator power, no, seamlessly supposed to be, right? And then once regular power is back, it does the reverse thing, no. Once regular power sinks back in, then it changes. No, sasaluhin uli ng UPS. Now those UPSs, I don't remember if the requirement is 1 hour or 3 hours. I can't remember lang eh. But a couple of things I've seen, there's a couple of things I've seen. One is for the more portable systems, they would have a portable UPS for it. And then they would have a bigger UPS for the whole thing. The only caveat naman that you have for UPSs is the maintenances and the batteries. No? So the more modern ones, I'm pretty sure they have monitoring as well. Oh, by the way, for medical applications, there are specific UPSs as well, because with UPSs you can also start introducing leakage capacitance. So that's why there are specific medical UPSs. I think Schneider offers that as well. No, I'm not so sure. So there.
Thank you very much, sir. Are there any other questions? You can just unmute your microphones and direct the questions to our speaker, Sir Vincent. Sir Arlon says thank you to your reply, Sir Vince.
Oh, thank you very much. You're welcome.
Yeah. Are there any other questions? You can just unmute your microphones, guys. Walang tanong?
Well,
About sir,
if there are no questions, it's two things. It's either I really sucked at what I did, or I was able to explain it properly. So chances are it's the first one.
I think it was just clear. You presented it clearly, and I could not see any other questions here. Oh, there's another follow-up question from Engineer Arlon. Sir, follow-up. The insulation monitors, do they require calibration?
Technically, no. Technically, no. Remember, they measure in through RMS, no? Technically, no, they don't require It's not required to have them calibrated, but there are instances where other hospitals, uh, want them calibrated. There are instances. So, of course, that can be sent back to the manufacturer to be calibrated. However, if you do that, you have to be able to replace it right away. Hindi pwedeng palalabasin mo sa bansa yung device, and then you leave your system unmonitored. So there has to be some sort of a replacement there. Uh, there were I think just one installation we've had where uh, it was the contractors and designers that required us to have a calibration certificate, calibration certificate together with the devices. So we gave that, and then our principals though wrote them a letter as well that these devices do not need to go back to Germany to be recalibrated after X number of years. No, hindi naman. Uh, so up until now, it's all of them are still working properly, and we haven't had a device that come back to us. Not yet, at least. Thank God, wala pa naman. So yeah.
Okay, thank you. Engineer Gemo from UAE is asking if we will be provided with a copy of the presentation.
Depends if you pay me. Yeah, no problem. Sure. I can give this to
Okay,
you.
and service can just send to our chapter, and then we will send it together with the certificates, guys. Please don't forget to register in the link provided here in our chat box, okay, for your attendance. In order for you to receive a copy of the press mat and your e-certificates, okay? Are there any other questions? Oh, another question from Sir Harvey from Oman, Sultanate of Oman, Sir Vince. What about its lifespan? Also, what are the enemies of those devices?
Okay. Lifespan, right? Lifespan. Well, it greatly depends on the operating conditions. No, that would greatly depend on operating conditions. Uh, for hospital purposes, no, for hospital purposes, uh, the first one we installed was back in 2011, and it's still working. No, at least for an IEC system. No, however, we have replaced a few. We have replaced a few line isolation monitors, the NFPA ones. No, the NFPA ones back in 2012. But those things are like 13 years old, 14 years old. That was never maintained in the first place. No, they never touched it. Nothing. So the lifespan is pretty long. I mean, if I'll be stringent about it, maybe it shouldn't give you a problem for 7 years, at least for hospital settings. For more, let's say, mas harsh ang environment, well, at least for vendor that comes with 2 years of warranty, uh, we we've we have a few uh, systems in a coal plant right beside the ocean, and it's still working. So, and that's been there since 2013. We have one in a hydro that no one touches. So, and it's been there a while na rin. So, yeah, the lifespan is pretty long, no? Uh, if if we're gonna be talking about what are the enemies, no, the threats behind insulation monitors are, I would say, itchy fingers. No, yung mga may makukulit na may makukulit na sumubok na kung anong gawin. No? So if there's an enemy to that, that would be it. No? The itchy fingers, and probably the worst enemy of this is not understanding what they're looking at. No? Because we've seen systems with alarms na zero na ang negative. Wala na. No? For these, zero na. In short, hindi pa lang nagtitrip, pero zero na. It's a hard fall to ground. And they're still there. It's like, Yung pala yun, fault pala. So again, that would be the worst enemy, is not using it properly. But otherwise, no known enemies. Other than itchy fingers and not understanding what you're looking at. That's it.
Okay, thank you, Sir Vince. Another question.
Sure.
Are the results obtained can be integrated in the BMS?
Yes, definitely, definitely. A couple of ways to have it done. There is that analog way of using the dry contact outputs, or you can take it out of a gateway using either Modbus RTU or TCP/IP.
Okay. There's another question from Sir June J. Perez. For hospitals lang po ba application ng mga devices po? Haven't heard kasi sa mga residential or commercial yet except for GFCI.
Yep. No, it's not exactly just for hospitals. Now, well, a couple of things. You can use the insulation monitoring device for any ungrounded system. It can be on a shipping vessel. It can be on a crane. It can be on mobile generators. It can be on an ungrounded DC system. It can be on a Delta system up to 20 kV. No, at least insulation monitoring. It can be on an AC system also for manufacturing. Now, more often than not, for the residential that we have, for the residential, oh, sorry, I forgot to mention, it can also be used for photovoltaic systems, since a lot of them have a battery system or on a DC stage. Now, you don't see a lot of that in residential now, because that wasn't really a target market for them. But let's say you have a high-rise condominium where you have swimming pools maybe or whatnot, things that get wet all the time. Yes, I would agree with you that they would usually have GFCIs, ground fault circuit interrupters. Now, for grounded systems kasi, what we use is basically a residual current monitoring device. Again, this is for mission critical facilities where instead, kasi the main job of a GFCI is to measure that non-zero balance of currents, and once it reaches that threshold that you've set, it's gonna magnetize it and activate the armature and open the circuit. That's its main job. And sometimes for mission critical, they don't like that because it always trips on them. But for, let's say, personal safety, human safety, yes, ginagamit natin yung GFCI. So the measuring principle of a residual current monitoring system and a GFCI is exactly the same. However, the only difference is that we have two alarms for residual current monitoring. One is the first alarm. Second is the threshold that you've set. The first alarm, the warning, can be set anywhere between 10 to 100% of that set point. So if I say for grounded systems na, all right, personal protection is deemed at 10 milliamps, kunyari lang, and I want to find out 10% of my set point, so at 1 milliamp, pwede na siya mag-alarm. So there. So it's usually the same. But yes, you usually don't find this in residential areas. It's usually in the more commercial, industrial, mission-critical areas.
Okay, thank you. There's another question here. Can your system be handled now by any licensed electrical practitioner?
Yeah, of course. Yeah. All you need is a bit of training, and then you're all set. I mean, yeah, of course. It's very easy.
Okay, thank you. And Sir Raimundo Belga Jr. is asking, ask ko lang po ulit yung company name niyo, sir. Thank you po.
Okay. Basically, I represent three companies. It's Westco Electrical and Equipment Corporation, VCP Trading, and PAMAV Tech. So just to give you an overview of who those three companies are, Westco Electrical and Equipment Corporation is basically a technical service provider and solution provider for generating companies, transmission, distribution, and heavy industrial. Are the usual customers we have are usually in the top 100 customers. VCP trading, though you hear trading, but they do have their exclusive products. So that's what they concentrate on. But they can sell pretty much anything under the sun. However, they've concentrated on heavy industrial as well as some of the distribution companies out there as well. PAMAV Tech is our training facility, no? So I'm sure a lot of you guys have heard of PAMAV Tech because they're noisy on Facebook. But yes, PAMAV Tech is our training facility. We're one of the few individual training facilities out there that can actually register your CPD points, no? So there.
Maybe, sir, you can post later your company name and contact number or contact
Yeah,
details
sure.
so that our
I
participants can contact you in case they
Of
require
course. Yeah.
some.
I don't know if my marketing assistant is online as well, so he can do that. Gab, do you mind telling to help me out there? Because yeah.
There's
Okay.
another question here, Sir
Sure.
Vin, from Sir Jose Limbaga Jr. What type of line isolation monitor does vendor offers? Ground detector type or dynamic ground detector type?
Oh, great question. And the answer is I don't know. The answer is I don't know because the kind of type they have inside is a tightly guarded secret. Really, even the leakage capacitance measurement formula is something I just stole out of something. But to be completely honest with you, I don't know. All I know is basically they just give you a calculated measurement that is going to be a little similar to a measurement of a GFCI. That somehow, at least how I understood it. Yeah. So sorry, I can't give you more details on that.
Okay, another question. Guys, if you want to know the contact details of Wesco, PAMAV, and BCP, it's already here in our chat box. And another question, Sir Vincent, from Sir Rolando Escanilla. Sir, sa LEED certified building, isa po ba sa ITMAS requirement?
I don't believe so. I don't believe so. I don't believe so. Um, Trying to remember kasi the classifications that's there, but I don't believe that it is required. Now, I'll try to get back to you guys on that. If you guys can put that question in particular, if you can put in your email or your number, I can try to find out. I just want to make sure because I don't remember seeing that kind of requirement for a lead building, no. But to be sure lang, I'll look into it again, no. Kasi mahirap magsalita tapos alanganin ako eh. But yeah, I'm like this right now, but as far as I remember, I did not see any kind of requirement for that. If anything, ang nakita ko is a proper power energy meter, if that's what you're, yeah. But I can get back to you on that. Yes, please. If you can send us that question, I can
Okay,
find out for
thank
you.
you. Thank you, Sir Vince. It's a question from Sir Rolando Escanilla.
All right. Sherwin, my marketing assistant is there. Sherwin, might please take it down and yeah, I'll try to find out for you.
Okay, Sir Rolando, kindly write down also your email or any contact details so that they would get back to you upon confirmation of the answer to your question. Any other questions, guys, that you may direct to Sir Vince? See, it's already our question and answer portion. He's very free to answer all your queries. And thank you, Sir Vince, for accommodating us.
Of course, my pleasure.
Okay, any other questions, guys? Just unmute if you don't want to type your questions. You could direct your questions to Sir Vince. Sir Gimo, yan. Sir Jaime is not here with us. It's always Sir Jaime who who ask questions?
Naitanong ko na yun sa akin kanina.
Nakapagtanong ka na, sir. Okay. Who else would like to ask questions to Sir Vincent? Wala yung isang suki natin eh. Wala si Sir Jaime yata ngayon eh. Baka binabaha na siya. Joke.
Wag
Huwag naman
naman.
sana.
Wag
Huwag
naman.
Hindi, malayo naman siya. Nasa Pangasinan siya.
Okay.
So, walang ulan ngayon doon. Okay, so wala na.
Na-press.
Yes, Sir Rodel.
Nagpe-prepare yon sa next stop niya.
August 19, nga, abangan natin yung talk niya sa August 19. Ikaw, Sir Rodel, baka may tanong ka kay Sir Vincent.
Wala akong tanong.
Wala.
Sir Gimo, kailan siya magtapak sa webinar natin?
Sino?
Si Sir Gimo.
Si Sir Gimo daw. Sir Gimo daw. Mag-speaker ka din.
Oh,
Okay?
ngayon na.
Okay, no more questions for Sir Vince. So in this regard, okay, we would like to award this certificate of appreciation to our speaker. Please know that the Institute of Integrated Electrical Engineers of the Philippines, Northern Laguna Chapter, just to emphasize again, the only chapter who is the best chapter Hall of Famer, awards the certificate of appreciation to Vincent Jason V. Peñalosa for sharing his technical expertise and profound knowledge as the resource speaker in this 2-hour webinar entitled Electrical Safety Critical Care Units, given this 22nd of July 2021. Signed, Rodel Manalo, VP Internal NLC, webinar proponent, March Machenzo, President of NLC, and yours truly, former President of IIEE NLC and the current National Treasurer. Again, thank you very much, Sir Vince. We will be sending this certificate to you. Thank you for accommodating us for a very short notice. Still, you are here with us. And again, hope to welcome you back again for another topic for our participants, a free webinar to all members of IIEE inside and outside the Philippines. So we've reached around 184 participants a while ago. So,
Wow.
yes, okay. So again, thank you very much. Palakpakan natin si Sir Vince. Okay, thank you VCP, Wesco, and PAMA. Best regards to Sir Roddy. Okay?
Of course, I'll tell him. Thank you very much, ladies and gentlemen. Maraming salamat. Have a good week.
Okay, thank you. Stay safe, everyone. God bless. May bagyo-bagyo pa. Sana maging maingat tayo. Okay? Stay
Salamat.
healthy.
Thank you very much.
Bye-bye.
Thank you.
Thank you po. Thank you.
See you again next week.